Newton. You know who he is?
Yeah.
Who is he? He's English. That's true. What else do you know about him?
It's explorer.
Yeah. Give me your English. Gravity? Yes. Yes.
I don't know.
Yes. Yeah. We don't know much about him, or it's hard to explain.
I think it's hard to explain.
Yes. Yes. He's very important. But what do we study when we study Newton's laws? Yeah. Yeah, so what is F? What's that called? Force. Okay, so that's what we're going to look at today. So we're going to look at Newton's three laws. Yeah. So, before I do the laws, I have to do some definitions. So, first definition is force. So, can anyone explain to me what force is? You know what I mean by force?
Yeah.
No? That's okay. You know
I
force?
don't want to give dimension.
Oh yeah? So, do you want to try? Don't be shy. So, Saeed, so you know force is like when you push something or pull something or hit something,
Yeah.
open the door, you use a force. So, you want to try?
The dimension.
Yeah, go on, try.
I don't know how to describe it.
Oh, that's okay. Do you know Abraham?
I'll try.
Try.
I think it's like you push against an object or
Yeah.
pull an object, the force is out.
Yeah, yeah. And Saeed, do you have at least know what we mean when we say force, like this word in English, force, F-O-R-C-E. Have you seen this word before? Is it a new word?
Yeah, I see.
You've seen it, yeah. So it just means, like as you said, push something, you push with a force, you pull with a force, you write with a force, you do everything with a force. Yeah, does it make sense? Or yeah. So, as it's a kind of a simple level, a force is. Now, this is a simple definition first. What a student might learn in elementary school. So, in elementary school, you might say a force is a push or a pull. Now, like I said, that's elementary school. It's just to get you picturing the meaning. You push or you pull something. That's a force. Okay. But now we can give definition now. So we say, and there's many different ways to give the definition. So one way, which is easy for me to remember, is a force of 1 Newton, 1N, acts on a mass of 1 kilogram if it causes the mass to accelerate by 1 meter per second squared. So the picture we have here is we have 1 kilogram and it's accelerating with an acceleration of 1 meter per second squared. If that's happening, it is because there is a force pushing or pulling it and we say this force is 1 Newton of force. So this is, the definition. Please make sure you write that down carefully, because in the exam, this is something they could ask you for like 1 mark, 2 marks. They might say, what is a force, or what is a Newton?
Push or...
No, sorry. Like I said, that's only for our understanding. Yes, it'd be much easier, but sorry, you can't. Okay, you got that written down? And the diagram too is useful. Yep. So, this week we looked at the equations for U, V, A, T and S. Yep. But we have not said what makes the A. And this is what makes the A. A force makes the A. So if you have a big force, then you have a big A. A small force and a small A. In this example. Okay? Now, there's some more definitions. Okay. So the next definition I want to give you is momentum. Okay, do you know this word? You do? Tell me what it is.
There's initial momentum.
There's initial momentum, yes?
I know the equation.
Yeah? Tell me what it means, the word.
It means push.
Sorry, not that. Abraham?
I think it's average now.
Average what? No, not this. Say it, no. It's to do with velocity, yeah. I'll give you the simple definition first. Momentum tells me how, the momentum of something tells me how difficult it is to stop. And what we mean is, if something has a lot of momentum, it's more difficult to stop it moving. The more momentum it has, the more difficult it is to stop. Okay? But there's a formula for momentum. We use the letter P for momentum. And the formula is quite simple. It's mass multiplied velocity. And we can see therefore the units. What would be the units for momentum here? It would be kilogram meters per second. Now, in words we can say momentum is the product of mass and velocity. Yeah. So let's have some simple calculations. So we'll have our car. What will we say the mass of the car is? Yeah, at least 1,000, maybe even more. So we'll say the mass is 1,000 kg, and the velocity we'll say is 20 meters per second. So momentum is, easy calculation here, 20,000 kilogram meters per second. So let's compare that with a person. Their mass, we'll say, is 90 kilograms, and their velocity, we'll say, is 5 meters per second. So their momentum would be 450 kilogram meters per second. So you can see which is more difficult to stop. Well, of course, the car is more difficult to stop. It's a lot more difficult to stop than the person running. Okay. So I think we'll go on to now Newton's first law. Does anyone know Newton's first law? What is it?
An object stays stationary or
Mhm.
speed unless a force is acting.
Good, yes. So this is Newton's first law, we'll write it down. So I'll just write N1 for Newton's first law. So Newton's first law is, as you said, an object will, you said stays at rest, that's good. So I'll say, or you said stationary, which is good. I'll keep the English a little simpler. I'll just say an object will remain at rest or constant velocity unless it, I want to keep the English simple, an object will remain at rest or constant velocity unless a force acts on it. Which word do you prefer, applied or acts? Acts, alright. Unless a force acts on it. Acts.
Stephen?
Yeah.
Moment equals m v, right?
Yeah.
That v is every velocity or...
We will only look at constant velocity, yeah, but we will look at averages later, yeah. But for the moment, yes, this is a constant v and a constant v for the moment. So that tells us that the car and the man will keep travelling at this speed unless a force stops them. Okay, now on to Newton's second law. The really, really, really important law. What's Newton's second law? Who knows that? Yeah. Newton's second law actually gives us a formula to calculate the F or the A. Newton's second law is F equals ma. That the force equals the mass multiplied the acceleration. Or in words, force is the product of mass and acceleration. And we'll come back to this in a moment. And finally, Newton's third law. Now, for every action, there is a reaction, yeah. I'll keep it simple. Okay, what's interesting is Newton's second law, we can relate it to momentum. So I'll show you the relationship now. But if you see here, if something has a big mass and a big acceleration, then we say it has a big force acting on it. Okay? Right, so I go down here. So let's just look at Newton's second law for a moment. We say F equals ma. But what's the formula for A?
V minus.
Yes, V minus.
U.
Yes.
Over
Yes.
T.
Good. And that is Ft equals mv minus mu. But what's mv? Momentum at the end, and here momentum at the start. So we can call this here delta P, which just means the change in the momentum. Okay? That's all this symbol means, is the change in the momentum. And then the T, we normally write it as delta T, and what we mean here is the small time that passes. So this here is just small time. I should write it here as well, small time. So we get this now new formula for F. We can say F equals delta P over delta T. What this means is, in words, is force is the change in momentum per unit time. So another way of thinking about force is how quickly the momentum is changing.
Is that T, it's mean small time?
Yeah. Usually less than 1 second. Now, you see this delta P here, this is actually important, which we'll look at it in a minute here. Yeah? Okay. So it's going down now. Oh, wait. It's okay, Saeed? Yeah? Okay. So remember that, oops, delta P, that's the change in momentum, yeah? And that's actually an important idea in physics. And you know something's important when it gets its own name. So it gets a special name here. We call it the delta P. Sometimes people call it I, but it's the same thing, okay, it's the same thing, and we call this the impulse. Is this a new word, or do you know this word? It's new? You've seen it before? Yeah. So I'm not doing anything there except telling you we can call change in momentum impulse. Okay? Now,
We can use it's in the formula.
yeah, in fact, if you're right, Saeed, you could write your formula now like this, I over delta T if you wanted to, or normally in the exam formula book they write it like this, I equals F delta T. So impulse is also the force multiplied the time. is another way of looking at it. So we've done lots of formulas, lots of definitions. So now let's look at some examples of how to use this. Let's see. So, we ready for examples? Yeah? Okay. So our first example is, we'll keep it nice and simple. We have here 4 kilograms, and let's say somebody pulls it with a force of, I don't know, 10 newtons. So that means this will start to accelerate. It'll have an A. Let's calculate the A. So that's my first question, is to find A. So, first part, F equals ma. So that means that A equals F over m. So here that will be 10 over 4. Yeah? So that would be 2.5 meters per second squared. That's okay?
If we need to find A, we change it.
Yeah, we can just rewrite it, yeah, like here to here. Yeah. Now, the next part, okay, so here's our same problem, okay, same problem. At the beginning, it's at rest. And then 3 seconds later, it's traveling with some velocity v. I would like for you to calculate the v. Okay, so using your formula this week, give me the v. You know the A now. Here's the A here. That's the A.
V equals U plus AD.
Yep, hasn't changed. You get the V? What did you get? 7.5, yeah. Yeah, so the V here now is 7.5 meters per second. So the reason for doing that is I'd like to calculate now the impulse.
So how do we call your final velocity?
What do you mean? Just final velocity. That's all, yeah. Impulse. What impulse? What did I say impulse was? What? Yeah, what did I say? Change in momentum, which is mv minus mu. Now what's the m here? What did I say the m was? 4. And the v? 7.5. And the u? 0. So what's this number here? It's going to be 7.5 plus 28, 30, isn't it? Yeah. 30 kilogram meters per second. So that's the impulse. Yes? Now I want to try and connect this back to the start. What does the force equal for this problem? What's the force? I give it to you. How much force is it? 10 newtons, yeah? 10 newtons. Can you give me another formula for our impulse? So we have impulse equals 30 kilogram meters per second. Do you have another formula for impulse?
Yeah.
What is it?
I equals FT.
Yeah, you have another formula for impulse. It's F delta T. That should equal 30, yes? Now, what is the time here? 3. So you got 3F equals 30. So what does F equal? 10. Now, you don't need to write this down. I'm just showing you that you still got the same answer that was in the question. So all these formulas, you know, they relate to each other. Okay, let's look at one that's more difficult. So I just really need you to take note down to calculate the I. Okay. Let's do another one. Can I scroll down? Yeah. Okay. So another example. All right. So let's say we have a golf ball. You know golf?
Yeah.
You know the sport, yeah? So you have a golf ball, and what would you say the mass is of a golf ball? What should we say? It's not going to be small, isn't it? What number do you think? 10K? 10 kilograms? 10 grams, maybe, yes. 0.010 kilograms. Yeah. Okay, and we'll say that we have our golf club. Now, when the golf club is here, there's no force because it's not touching it yet. But then later what will happen is, it will hit the golf ball, and then it will move the golf ball, and then the golf ball leaves. So there's a small time here, we'll call it delta t, when it touches the ball. It gives it a force. And the time here is only going to be, we'll say, 20 milliseconds. Milliseconds, quite short. Okay? And we'll say that the speed here is 30 meters per second when it leaves. And at the beginning, of course, it's 0 meters per second because it's at rest on the ground. So what I would like you to do for me first is I want you all to calculate the change in momentum. The change in momentum. What's the other word for this?
Impulse.
Impulse. So calculate the impulse for me. We got the impulse?
0.3.
Yeah, you should be using, this formula here, because you know everything there. Only 0.3? I would have thought it was bigger. Are you sure?
I was sure.
You were sure until I asked you. Impulse is mv minus mu. What's the m? 0.01. What's the v? 30. And then the 0.01. And then the u? 0. Oh, okay. I guess you're right. So it'll be 0.3 kilogram meters per second. Yeah. Right, the next thing I want you to do for me is tell me the force applied to this golf ball. How much force was applied?
Meaning there's power minus 3.
Correct.
Which formula?
You will have to use impulse equals force multiplied time. Do you have that formula written down?
Yeah.
Yeah. Is this a big number or a small number?
I don't know if
What is it? It's big for like a small golf ball, yeah. I don't know, I think we made our golf ball too small. I think maybe it's more than 10 grams. Maybe more like 50 grams. Anyways, no problem. Let's calculate the force now. So we have F delta T equals impulse, which equals 0.3. So F delta T equals 0.3. So F equals 0.3 over delta T. So F equals 0.3 over 20 milliseconds. Yes? So, what's this going to be? No, let me think. I can do this in my head. 5, 15... No, I can do this. 1.5 times 10 to the 3? Maybe? No, alright, tell me what it is.
15. Sure.
Exactly 15? Oh yeah, okay, because it's going to be 300 over 20, isn't it? Yeah, 15. Yeah, of course. 15 newtons. That's not too much. Okay, go on and look at another example now. An interesting one maybe you can have experience with. You had experience with. Can I scroll down?
Where are we?
The 20?
No. 20 and 10
This?
square minus 3.
Yeah, this is given in the question. Let's see. There.
Okay. This is the time.
This is the time, small time, yeah. So that's it, that's all it is.
10 is a square of minus 3.
Because it's milliseconds, yeah. Okay. Right. Can I go down, Saeed?
Yeah.
Yeah, okay. So let's have an example here. You've all jumped from a wall before, right, as children? I'm sure you have. Yeah? Yeah. So, how high do you think is the highest wall you've jumped from? What did you say?
From the...
Yeah.
3 meters.
2 meters? 3 meters? 1 meter? What?
Half a meter.
Half a meter? What would we say? What's the biggest wall you think you've safely jumped from? 6 meters? 2 meters, we'll say. Okay, alright. So when you're... so how old were you then? How old were you? 10? 11? Maybe? So what mass will we make you have when you're a child? What would we say your mass is? 35, okay. So first what I want you to do for me is tell me in this problem what is your speed before you hit the ground, your v. So you have to use the g here, the acceleration. Do you remember what it is from yesterday? The acceleration from gravity? 9.81 meters per second squared. And we'll say that you start at 0. So tell me the v, please. You'll have to use v squared, I think, formula. So you get, what's your square root 2 root g? So what's that, about 6, is it? 6.2. Okay. So good job, you got the v, it's 6.2 meters per second. Now what happens to your legs? What do you do with your legs when you land on the ground? So if you picture landing on the ground, what happens to your legs? Do they stay straight?
No.
Now what happens? What's the verb? What happens to your legs when you land on the ground? Do you keep your legs straight like this?
No.
Now what do you do with your legs?
I don't know that word, but
Don't know the verb?
Crouch.
Yeah, okay, you bend your legs. Bend your legs. So, when you land, drop like this, you bend your legs. And if you think about the golf ball, for example, or like this here, if you just slide this to me, yeah, I'll give it a good push. No, really hard, so it hits the pen. Oh no, it's not fun. Oh no, just try again. Okay, the force, I only use the force to slow it down, but once it stops, there's not really any more force slowing it down. Do you understand? It's like with the golf ball, okay? So I hit the golf ball, but then as soon as it leaves, there's no more force. It's only while it's touching. And like when the person is landing on the ground, okay? So when they fall and their knees are bending, the ground is pushing up to slow them down, and then they stop, and then the ground isn't pushing anymore. So it's hard to picture this, because we think the ground is not moving.
Yeah.
But when you're landing, it's like the ground is pushing you up, like how I push here, okay? So what we want to calculate is how much, where's my pen gone? How much force the ground is giving you to slow you down, to stop you, okay? Now, what I want you to do now for me is calculate the impulse now for this boy. It is 217 kilogram meters per second. Okay, what formula could I use now to find the F? I could say F delta T equals I. So now I have F delta T equals 217. Yep. So now I have F equals 217 over delta T. So there's one more piece of information we need to solve this problem, and you give me the number. Tell me, what do you think? How much time do you spend bending your legs and slowing down when you hit the ground? It's going to be small.
Yeah.
So what do you think?
1 minute? Oh.
1 second, baby.
yeah.
What do we think? 1 second? When you hit the ground, your legs bend and then you stand straight back up. 3 seconds, I think, maybe too long. Still too long, I think. I think it'd be less than a second. Maybe half a second. Half a second, I'd say. I'd say half a second. So now, if you put half a second in here, tell me what you get. 434 newtons. Now, this is quite interesting because I'll circle it in red, and then I'll circle this in blue, and then I'll circle this in black. That's That 217, how did you calculate that 217? How did you get the 217? Yeah, it's the MV minus MU.
Yeah.
Now imagine you're this boy. Can you change your V? You can't. What gives you the V? How did you get your V? Why are you going faster? Because you're falling. So can you change your V? No. Can you change your U? Well, you could. But I mean, you start at rest, so you can't really change your U. It's like you fall. So you can't change this 217. But this, what do you think? Can you change this? What do we think?
What?
The delta T, can you change that?
Yeah.
You can. No, you can. Yeah. Because the delta T, you can change. For example, if you keep your legs very straight when you hit the ground, then the time is really small. But if you bend your legs when you hit the ground, you make the time, the delta T, bigger. Yeah? So what do you think happens? If I make the delta T bigger, what happens to the F?
Smaller.
No. Oh, yes, sorry, smaller. Yes, sorry, smaller. If I make the delta T bigger, I make the F smaller. And likewise, if I make the delta T smaller, I make the F bigger. Now, what do you want? Do you want a big F or do you want a small F? You want a small F. Because the F is what you feel in your legs. So how can you make the F smaller? You make the time bigger. And how do you make the time bigger? You bend your legs more.
Yeah.
So this is why it's important to bend your legs as much as you can, because you make the F smaller. Okay? So this is a good example of using impulse and force, and maybe something you have experience with. When you fall, you feel like you should always try to bend your legs when you land on the ground. It's an instinct. It's natural. And this is the reason why. It's so you feel less force in your legs when you hit the ground. Yeah? Okay. One more example to do now. Oh yes, and another thing as well that helps the delta T, the ground. If the ground is soft grass, you increase your time, because you know, if the grass is wet, you kind of sink into it a little bit. The grass is kind of stretchy. But if it's like concrete, you know, if you drop something on concrete, it's a smaller time, because it's a smaller time in contact. But if it was something like this, you make the time bigger. It's more time spent in contact. So that's also, you know, if you fall on sand, is better than falling on, you know, concrete or something. Yeah? Okay, another example now. Okay, go down. It's a rocket. It doesn't matter, it's a rocket or, well, we'll do a rocket first. There. It's an American rocket now. Okay. We have here a force going up, of course, and then we have a force going down. Now, what's the force that's going down?
Pushing.
Yeah, what's this force called? Yeah, what's it called?
The action.
No?
Result.
Begins with a W?
Weight.
Yes. So, you know, the earth is pulling something down. We call this force the weight. Okay, so for example, here, this falls down because the earth pulls it down. We call this the weight. So if this rocket wants to go up, we need the force to go up to be bigger than the weight.
Yeah.
Okay? So if we have this result now, If this force is going up and this weight is going down, then the total going up would be F minus W. That's the force then, in total. Because it's like this cancels some of this. Okay? And of course, if you have this, then it's balanced. Nothing happens. But what I'm going to look at now is, how can we calculate this for a rocket? And it depends on the gas that comes out. That's what we're going to look at now. So this is now us using, we'll have to use Newton's third law here for these problems. Okay, can I scroll down? Yeah. So it's not just for the rocket, it can be anything like a rocket, but we'll do the rocket first. The rocket works, I'm sure you know this, because lots of hot gas gets pushed out of the bottom. And when this happens, it causes a force to go up. Now, how can we get the force? Well, let's put in some symbols here. Let's say for every delta T, there's a delta M of gas that comes out. So, for example, I might say something like, 100 kilograms of gas per second, something like this. So in this case, the delta M would be 100, and then the delta T would be 1. It's saying every second 100 kilograms comes out. But of course, we also would like to know how fast it's going, because we think if it's going faster, then it makes the rocket go quicker too. So let's see if we have a formula here to calculate this. I'm trying to think of an example where maybe you can experience this. Anyways, we have here a formula for F that equals the change in momentum over the change in time. We know this formula. Now, what is momentum though? What's the formula for momentum? It's mass by velocity. So the change in momentum will be the mass times the velocity, the change in velocity over, hang on, something's wrong here. Sorry, I shouldn't be, oh no, that's fine. So, sorry, let me just go back a tiny bit here. This is over delta T. Now, for these problems, okay, they always do it per second. So that means the delta T will be 1. So we can say here, for the gas, it's just equal to this. But what's the momentum of the gas? What's the formula for momentum? mv. So I have m and then v. In other words, I'm sorry, it looks a bit messy, but I'm trying to get this formula here, that the force is equal to the mass per second multiplied by the velocity of the gas. So in fact, if I go back up here, Newton's third law says that when the gas goes down, it would cause the rocket to go up. And the force that's going up, we have a simple formula for it. It's the mass per second of the gas multiply the velocity of the gas. This is the force making the rocket go up. And this has a special name. This force that makes rockets go up, we often call it the thrust, but it just means force. So here's the formula. It's the mass, well, I'm just writing it again, the mass per second, and I should really say velocity per second, velocity in seconds, in meters per second. and then this is the mass in kilograms. That would be the thrust in newtons.
Essentially, the force of the just long jump is the same as the force of going up.
Yep, yeah. Yeah, that's really it. From Newton's third law. Now, what's really interesting is it doesn't need to be a gas. It could be anything. So I have this video at home. It's a pretty funny video. Sorry, can I go down? Yeah. This person here, he had on his backpack, you know, backpack? And in the backpack there was 2 hoses, and out of the hoses came water, and he had this connected up to a water supply, and the water was coming out really, really fast, and actually this made him go up. So he's sitting here, and the water's going, and then he starts to go up. It's funny. So let's try and do something like this as an example. So, how heavy are you? What's your mass? Do you know it?
60 kilograms.
60 kilograms. Do you know yours? What is it? 51?
Me? I'm not sure.
It's probably more than that, yeah? So we'll make it 51 then. Okay. So, let's calculate your weight. So the weight first. What's the formula for force? It's MA. Now, what's your M? 51. And then what's the A? That's not G, 9.81. So here we have this formula, by the way, for weight. Can you tell me what that is? 500, we'll say 500 newtons. Okay, so we want to build you a backpack, and we send the water coming out. So if I want you to go up, how much force do I need? I need more than 500 newtons for you to go up then. Okay. How much water do you think we can release per second? What do you think we could do? What do you feel like? How much water do you think we can shoot out per second? How many kilograms? Just what do you feel? What do you think? Maybe 2 kilograms per second, do you think? Like 2 kilograms would be about 2 bottles of water. I think we could do better than that. What do you think? Maybe 10 kilograms a second. So for this, we'll say that we can do 10 kilograms per second of water. Now, how fast do you think we can make this water? Well, let's just call that X, and let's find out how much we need to make the X so we can make him fly. So we'll say 500 equals 10 multiply X, because remember it's the mass per second times the velocity. That's how much force we'll get. Right, so what must the X equal then here? It must equal 50. That's a lot, isn't it? That's very fast water. I don't know if we can do this. I think we might need to make more water per second. Okay? So it's quite difficult to do this with water. It'd be much easier to do with gas, because you can make gas go really fast, can't you? Like a lot of gas can come out very quickly. But I'm saying, you know, it's not special for rockets. It doesn't need to be a rocket, okay? It could be water. It could be anything, you know. It's just gas is easy to make it go very fast. That's the key, why gas is used. But you can do it with water. You could even do it with solids, you know. For example, if I go down here, Imagine I have, I don't know, coal. Do you know coal? You must know coal, you're all from the Middle East, you know what coal is, don't you? So imagine I have pieces of coal and I throw the coal out, I throw the coal down. Now it's really, really hard to picture this, but believe it, if I stand here and I start throwing coal down, if I throw it fast enough and quick enough and enough, then I'll start to slowly move up. But I think I would have to throw it very fast. So let's say I can do, I don't know, 1 kilogram per second. And I would like to make 500 newtons again. So I would need 500 to equal 1 multiply the speed, which is x. So how fast would I need to throw this coal? 500 meters per second, which is kind of difficult to do, right? I can't really throw this at 500 meters per second. But if I could throw this at 500 meters per second, I would start to move up. Well, no, not me. You would start to move up. So this is an example of Newton's third law. Okay? So we've done Newton's second law, we've done Newton's third law. We haven't really said much about Newton's first law. And that comes up in more detail later. But Newton's first law just really says, you know, if this is at rest, it will stay at rest, unless a force acts on it. Or, if this is moving at constant velocity, it will stay at constant velocity, unless a force acts on it. That's all. Okay, so there's nothing, for the moment, nothing useful from that. That comes in that's more useful later. Okay, just make sure I got everything here. Yeah. So, just to be clear, we said Newton's second law is F equals ma. Okay? But just so you know, there are many, many different ways to say that. So we have one way of saying it, F equals ma. Another way of saying it is force is the product of mass and acceleration. Now that's not interesting because that's the same as that. But another way of saying it, we saw earlier today, is force equals the change in momentum per change in time. That's one way of saying it. But just so you know, and you can look this up online, there are actually many more ways of expressing Newton's second law. It's just that the most useful for us is this one and this one are the most useful for us. Okay? But don't think that this is the only way of saying it. There are many ways. There's maybe 5 or 6 ways of saying it. They all have the same meaning. Okay?
But if we need to find a moment,
yeah.
The change for moment, delta, we use the mv minus mu.
That's it, yeah. That's how you find the change in momentum, mv minus mu. Yeah, so you're right, Saeed. You could even write this as mv minus mu over t. It's the same. Yeah. Now, we will do, this is only the start, because we'll do more about forces, you know. We'll do things like going up a hill, going in a circle, you know, it gets more complicated. So this is just to get us started. How are we doing for time? Oh, good, okay. So what we'll do, I'll let you do this now then. And then tomorrow will be a tutorial. And so in tomorrow's class we can do problems from this one, or time velocity, or projectiles. So we'll probably need the full class tomorrow to do the 3 different worksheets, because I think there were problems on all 3. Yeah, you have the last part here. You think no problems in this one?
After I check the answers,
yes, that's a good point actually. So first I'll give you the answers. And don't forget actually, sorry, I forgot to tell you this. There's actually one more question. Oh no, you don't actually, because you don't have time. Yeah, here's the answers. for the projectile, and there's one more question at the top as a bonus. Okay. Yeah, one more. So these are the projectile answers, okay? Now, can I give one, who will see Louise? You're all in our class, so you can give that to Louise, and you can give that to Ugo then, if you see him then. Okay. So that's for projectiles, that's the answers. And now let me give you the Newton's Law ones to do for today. There are 9 questions. Yeah, 9 questions. Here you go. And I'll give you Louise's. Here, it can be your turn to give this one to Louise and Ugo. They share the work. Okay. Right, so you can do those now, and your homework will be to finish them. But these questions, as you can see, they're not as long as the projectiles. They're kind of shorter questions. So I actually think you could probably finish them now. Today, I mean. But if you don't finish them, I need you to do them for homework then. Okay? So you can start them now.